Good morning, everybody. Hope you're all healthy and safe at home. We are going to move back to our third module, and we're going to discuss about the concept of triple integrals in this section. So, section 9.15, triple integrals. So, in this section, we are going to deal with the integration of functions over a region. Okay, like we are going to consider the 3D space, x-axis, y-axis and z-axis. So till now, so far we were discussing about double integrals, and we did about our usual line integrals. So let's just see what is the basic difference between this triple integrals and there are similarities, but the only difference is that we are going to discuss about integrating a function over a region, okay, in a 3 space. So if you guys can see in the textbook, if you guys can refer to figure 9.15.1, you can see that the region that we have marked is, we are denoting it by D. Okay, so this is our region D, and what we'll do is the region is actually the blue colored region, okay, not the boxed one. The blue colored portion is the region, is our region, okay. And what we are asked is, we are asked to find the triple integral of this particular region, okay. So in case of line integrals, what we did was we had a curve, okay, and we partitioned it. That was, we partitioned the interval, right? And in case of double integrals case, we had a region in a coordinate plane, okay. We had a region there, but it was in the coordinate plane, so we did not consider the z-axis. The third axis was not in the picture. So in that case, what we did was, we again that was a flat surface, so we partitioned it into rectangular boxes, rectangular regions, right? Further rectangular regions, and we took the limit of the norm of p and all those stuff. So here also we are having the same concept, except that here we have a 3D region, okay. There we had, till now we were discussing about a flat portion, now we are having a 3D region. So here what we do is, we partition the region into n subregions. So here the subregions will be boxes. So that's what you can see here, that is, this region is partitioned into various boxes, okay. And rest all procedure are the same, that is, we choose a point inside that box, and we we find the value of f of that point, that is the function which we have to integrate over this region. And there, in case of double integrals, we had delta ak or dak, okay, dA. Here we'll be having delta vk, that is the volume, because we are having a box, we are having a 3D structure, right? So when we are considering a cube or a cuboid and all, we won't talk about its area, we talk about its volume, right? We have its surface areas and all, but we talk about its volume. So here we will have the sum, that is, all the procedures are same, so I'm not just going to repeat it again and again. So here the summation, can you see the summation? The summation will be like k equal to 1 to n f of x k star y k star z k star into delta vk, not delta ak, okay. So this is actually the Riemann sum, and what we do is, we take choose norm p tending to 0, and we find that the triple integral will be as follows, that is, let f be a function of 3 variables defined over a closed region D of 3 space, and the triple integral of f over D is given by triple integral over D. F is a function which we have to integrate, f of x, y, z, dv is equal to limit norm p tend to 0 summation k equal to 1 to n f of x k star y k star z k star into delta vk, okay. So that is how we actually that is the basic theory behind the triple integral concept. Now we cannot always partition a given region in 3 space, and drawing a region in 3 space itself is a bit difficult, but so we cannot think about the partitioning of it. And also what we'll do is, we evaluate this triple integral by evaluating the double integral of an integral. Okay, so let me just make it clear. So this is how we evaluate it. What we do is, the region, we are given a region, and just refer to this figure, okay, which is 9.15.2. so this D is our region, okay, and it is bounded above by a curve z is equal to f2 of xy and below by the curve z is equal to f1 of xy. So the region is closed, so it will have definitely a boundary. So it is bounded below by the graph z is equal to f1 of xy, and it is bounded above by z is equal to f2 of xy. Okay. Then what we can do is, we can express this triple integral as the double integral of the partial integral of this function. I hope it's clear. Okay, this double integral, a triple integral over D, can be considered as double integral over R, integral over f1 of xy, f2 of xy, that is a variation of z, f of xyz into dz into dA. So now this portion is familiar to us. We had been doing this all over, right? Double integrals. So this is how we can convert the triple integral into double integral. Now D is our region. So what is R? R is nothing but the projection of D onto the xy plane. Okay, here we are discussing about xy plane. So I hope you can see it. So this is our D, and R is actually the projection of this portion over the xy plane. So we get R. Okay, then the rest of the things are same. Once we know the region R, and we know that here you can see that it is of type 1. Okay, if the region is of type 1, then there is a variation from A to B. X is varying from A to B, and Y varies from g1 of x to g2 of x. So this triple integral over D, f of x, y, z, dv will be nothing but integral A to B, integral g1 of x to g2 of x, variation of y, and the variation of z, that is f1 of xy to f2 of xy, f of xyz, dz, dy, dx. Okay. So I hope this much is clear. So evaluating the triple integral, what we do is, we convert it into the double integral form, so that we can make it more easier, and we are comfortable with that type of integration. Okay, so now if you see, there is a difference between the double integral and triple integral. In double integral, we had dy dx or dx dy. Right, there was these two options, only these two options were available, and we had done some problems also, like change the order of the integration. But that is not the case in case of triple integrals. We'll have many options, that is dz, dy, dx. Not only that, we have dz, dx, dy, dy, dx, dz, dx, dy, dz, dx, dz, dy, dy, dz, dx. So there are many possibilities of the many, in the sense there are actually 6, that is 3 factorial possibilities of possible orders for integration. So we can change the order in whatever suitable manner that we need. So here they are just explaining it. Here we had discussed with dz, dy and dx. So here what will happen in this case, if the projection is onto the zy plane, yz plane, so that is how this thing comes out. So in this case, we have, this is our region in 3 space D, and that is figure 9.15.3, that is what I'm referring to. So this is our region D, and we are projecting it onto the yz plane. Okay, so here we will have the variation of y from C to D, and z varies from k1 of y to k2 of y, and x varies from h1. This is the boundary of the region. Okay, that is, it is bounded by upper half, and the up graph on the above on the left side and right side. So that is how we can change the order of the integration. So this is how we are going to deal with triple integrals. Now as similar to those of the things, the formulas that we have done in double integral, we have the same formulas in case of triple integral also. So you guys can just go through it. That is the volume. If f of x, y, z is 1, then volume is triple integral over d dv. If rho is the density, then mass of the solid D is given by m is equal to triple integral over d rho of x, y, z dv. Then we have the first moments. So here we'll have three moments. First moment, that is mxy, that is triple integral over d z into rho of x, y, z dv, and mxz would be triple integral over d y into rho of x, y, z into dv, and m of y, z will be equal to triple integral over d x into rho of x, y, z into t. And with the help of these first moments, we can find the center of mass, that is x bar will be equal to m y z by m, and small m, where small m is the mass, and y bar will be equal to capital M x z by small m, and z bar will be equal to m x y by small m. Now if rho, that is the density, is a constant, the center of mass will be the centroid. Okay, so center of mass is a point. Now we have the second moments, it is called the moments of inertia. So here also we'll have three moments of inertia, ix, iy, and iz. So ix will be y square plus z square. So till now we had ix was y square into rho of xy into dA, right? So here we have triple integral over d y square plus z square into rho of xy z dv. Iy will be equal to triple integral over d x square plus z square into rho of xy z dv, and iz will be equal to triple integral over d x square plus y square rho of xy z into dv. And we also have the radius of gyration, that is rg will be equal to the moment of inertia, whichever is being asked, divided by the mass root of, okay, square root of moment of inertia by the mass. So now we'll just discuss two examples, and we'll just see how we can apply this triple integral. So here the first one is, we are asked to find the volume of the solid in the first octant bounded by the graphs of z is equal to 1 minus y square, y equal to 2x, and x equal to 3. Okay, so first of all we have to draw the figure. So for that, z is equal to 1 minus y square will be a kind of parabola stuff. So this is our portion, 1 minus y square, z is equal to 1 minus y square. Okay, and we have y is equal to 2x will be a plane, the pink one, and that is we have this whole region right till here, and y equal to 2x cuts this region, and we have it is bounded by x is equal to 3. Okay, so we will take a small portion and we will project it onto the xy plane. Okay, and we will see what is gonna happen. So here z actually varies from the point 0 to z is equal to 1 minus y square. Okay, so the variation of z is clear. Now if we project this region onto xy plane, you can see figure 9.15.4b. okay, so we'll get a rectangular portion. And what will be the variation of x? X actually varies from this point. This is the solid region that we have to find, right? So the x varies from this particular point to x is equal to 3. So what will be x over here? X is nothing but y by 2. Okay, so x varies from y by 2 to 3. And what will be the variation of y? Y, it varies from 0 to 1. Okay, so we have got all the variations, so we can find the volume. Volume is nothing but triple integral over d dv. So here first we'll see the constant one will be put in the last. Okay, that's how we can find a particular value. So here first will be dz, which varies from 0 to 1 minus y square. Then we'll have dx, which varies from x varies from y by 2 to 3, and dy, which where y varies from 0 to. Okay, now we just have to integrate this. So dz1 into dz is z itself, so the variation will be 1 minus y square into dx dy, where integral y by 2 to 3 and integral 0 to 1. Now the integration of 1 minus y square with respect to dx or with respect to x will be x minus xy square, the limits being y by 2 to 3. We'll substitute this value, so it will be 3 minus 3y square minus y by 2 plus 1 by 2 y3 y cube. So this integration is pretty much simple. So the main difficulty that we'll be facing is to just understand the region. So for that we'll have to plot the region perfectly, and we'll have to have a clear picture of it in our minds. So this was a bit simple. We just had the parabola portion, and we did not consider any other section because we were asked to find the volume in the first octant. So we just have to discuss about the first portion, first area. And then we had a plane y equal to 2x, which cuts that parabola portion, and we had a boundary for x also. So that is how we can find the volume of the given solid. Now we'll discuss just one more example, that is the valuation of the changing in the order of integration. So here change the order of integration in the integration is like 0 to 6, 0 to 4 minus 2x by 3, 0 to 3 minus x by 2 minus 3y by 4, f of x y z dz dy dx to dy dx dz. So the original order is dz dy dx. We have to convert it into dy dx dz. Okay, so now the figure is given to us. We can see that we are considering the plane 2x plus 3y plus 4z is equal to 12. Okay, 2x plus 3y plus 4z is equal to 12. So that is our figure 9.15.5a. Okay, so this integration was dz dy dx. So we'll have z as a variation from 0 to 3 minus 1 by 2x minus 3 by 4y, and we'll have the variation, we'll project it onto xy plane, and we'll get type 1 region. And here y varies from 0 to 4 minus 2 by 3x, and x varies from 0 to 6. Okay, so that was our given integration. So how can we convert it into dy dx and dz? Okay, so here dy dx dz means first we have to integrate the given integral with respect to y, right? So we'll have to first find the variation of y, right? So you guys can see figure 9.15.5b. that is how we have changed it. That is we are actually projecting this region, this region d, that is the plane, onto the xz plane. Okay, so given it was projected onto xy plane, so here now we are asked to project it onto the xz plane. So here what will be the variation of y? Y will vary from 0 to, the plane is given to us as 2x plus 3y plus 4z is equal to 12. So what will be the value of y from this? Y will be nothing but 12 minus 4z minus 2x whole divided by 3, right? That is 4 minus 2x by 3 minus 4z by 3. So that is the variation of y. Then what will be the variation of the next one is x. So in that case we have already considered y, so you can remove this y from this plane region and just see what will be the variation of x. X will be nothing but 12 minus 4z by 2, that is 6 minus 2z. So x varies from 6 to 2z. And in the last portion we have z, so remove this x and y, and what will be the variation of z? Z varies from 0 to 12 by 4, that is 3. Okay, so I hope this is clear. So that's how from how corresponding to the figure we have got the plane, equation of the plane, and from that we can change the order of integration in whatever manner we like, and that is how we can evaluate the triple integral by changing the order of the integration. Okay, So usually, like previously in double integrals also we had discussed about the same thing. In some cases, if we integrate with respect to x first, the integration may be very complicated, so in that case we'll change the order. So here also, depending on the figure, in some cases the integration depending on a particular given order will be difficult. So if we change the order of integration, our calculation may be a bit more easier. So that's it for today's session. Thank you. Stay home and stay safe.